All right, hello again. So now I want to take a little bit of time and go through these heat transfer calculations and how to do them and how to use your reference tables to help you do them and the steps that you want to go through when you're carrying this out. So we talked about energy being transferred from one substance to another, endothermic, exothermic, all that stuff. But now we want to actually look at how to actually quantify, to measure the amount of energy that's coming in or going out of a system during some sort of either temperature change or phase change that we'll talk about as we go through. So as energy is being added or released from a system, we want to be able to calculate exactly how much energy is being produced or consumed in that process. So how do we go about doing that? Well, before we get into that, here's a couple of terms that you want to know. So if you want, you can pause the video, copy these terms down in your notes, and we're going to use these as we go through the material, right? So the heat of fusion is how much energy is needed to convert 1 gram of a substance from solid to liquid. So as we go from the solid to the liquid phase, how much energy is being, how much energy does it take to take those particles and pull them away from each other as we go from the solid to the liquid phase, right? If I have 1 gram of a substance, how much energy does it take to pull those particles away from each other? All right, that's the heat of fusion, and we'll abbreviate that H sub F. Okay, and you'll see that again on the next slide. Now, the heat of vaporization, remember what vaporization is. We're going from liquid to gas. So that's how much energy it takes to go from the liquid to the gas phase, to take the particles in 1 gram of a substance and pull them even further apart and go from the liquid into the gas phase. So that we call the heat of vaporization, or H sub V. It's one variable. Right now, the specific heat capacity, right, the symbol for this is going to be capital C, is the energy needed to raise the temperature of 1 gram of a substance by 1 degree. So now, if we're in a single phase, how much energy does it take to speed those particles up enough that their temperature is raising by 1 degree? So that's the specific heat capacity. Okay. So those are some terms that we need to know. So now, anytime you get one of these problems, you want to ask yourself a question. You want to say, okay, what is changing? So there's two possibilities. Either the temperature is changing or the phase is changing. So it's either one or the other. Right? Think about our heating curve, and we'll come back to this as we go through it to help you understand this. Okay. So here's our three options. These are our three formulas that we're going to use. And these formulas are on your reference tables. They're on table T. So if you take a look at your reference tables on the back, right here they are down here. It's a section that says heat. They're right there. All right, so these are on your reference tables. So take a look at your reference tables and you can see that. There's more stuff on your reference tables that are going to help you out with this as well. So these are your three formulas that we're going to choose from. All right, so if temperature is changing, you're going to go with the only formula that has temperature in it. That capital T stands for temperature. And if your phase is changing, you're going to want to go with one of these two. All right, so it all depends on what phases you're transitioning between when you're trying to determine whether to use this formula or this formula. All right, so remember, HF, that's heat of fusion. We just talked about that before. So fusion, solid to liquid. So you're going to use this formula if you're transitioning between the solid and the liquid phase. And then you're going to use this formula, HV, when you're transitioning between the liquid and the gas phase. So it's one or the other if your phase is changing. So you're going to look for keywords. Doesn't matter which way you're going, solid to liquid, liquid to solid. If you're transitioning between liquid and solid, use MHF. If you're transitioning between liquid and gas, use MHV. Okay? And I'll help you out with that as we go through it. All right, so what are all these variables? So these are on your reference tables too. All right, so Q is your heat transferred. And the units that we will use for that is the joule. Right? The joule is our unit for energy in chemistry. There's other units that we could use, but this is the main one that we're going to use. M is mass. Oh, goodness. M is mass, which we'll measure in grams, little g. HF is heat of fusion. We talked about that already. And that will measure in joules per gram. So how much energy per gram? Think back to our definition of the heat of fusion. Energy needed to convert 1 gram of a substance from solid to liquid. All right, heat of vaporization is the same thing. That's joules per gram. And then C is our specific heat. And our units for a specific heat is joules per gram Kelvin or joules per gram degree Celsius. Because remember, a Kelvin degree and a Celsius degree are the same size. So you can use either one interchangeably, depending on what your units for temperature is, which is usually Celsius. And then delta T is our change in temperature. Delta means change, this little triangle. The Greek delta, that triangle, stands for change. So that's our change in temperature, which we'll measure in Kelvin or Celsius. All right. And then the other thing we want to keep in mind is if it's water. Right? If water is the substance that we're using, then there's more information on our reference tables, table B. So if you look at table B on your reference tables, it tells us the heat of fusion for water, the heat of vaporization, and the specific heat. So this is huge, right? This is a big help in this topic. So you got table B on the front, right here. It's got these values for water, and then you got table T on the back that has your formulas. So use your reference tables. There's a lot of stuff on there that's going to help you out. Okay. So now how do we do these problems? All right. So here's the math problems that we're going to go through. And again, you want to kind of think about where are you on the heating curve? What is changing? Phase or temperature? That's the question you want to ask yourself. What is changing? Phase or temperature? So let's look at this one. How many joules of heat are needed to raise 10 grams of water from 45 to 95 degrees Celsius? All right. So whenever I do these questions, I like to be nice and neat and organized. So I like to let's go. I write out the equation. First thing I want to do is write out the equation that I'm using. 2, I want to list my variables. 3, I want to fill in what I know. And then 4, you want to plug that information into the equation and solve. All right. So here's our steps to success. Okay. So let's go through that as we're doing this. Number 1, how many joules of heat are needed to raise 10 grams of water from 45 to 95 degrees Celsius? So we want to say what is changing, phase or temperature. And look right here. We're going from 45 to 95 degrees Celsius. Our temperature is changing. So that means we want to use Q equals MC delta T, right? Our only formula would change in temperature in it, right? So now let's list our variables. I'm going to write it down here so we got some room. Q, M, C, and delta T. So here's our variables. So now what do we know from the statement, right? I know the mass, 10 grams, right? I know the delta T, we're going from 45 to 95, so 55, 65, 75, 85, 95. So we're changing by 50 degrees Celsius, right? And I also know my C. How do I know that? Because what's the key word here? Water. So remember, if we're using water, don't forget to use table B. All right, don't forget about good old table B off your reference tables to help you out. Table B. So use table B. It's a huge help. All right. So we know our specific heat is 4.18 joules per gram degree. All right. Can you pick the phone up so it stops ringing? There we go. All right. So we also know our specific heat is 4.18 joules per gram degree right off of table B. All right. So now what am I solving for? I'm solving for Q. So my unknown is Q. So now let's plug in what I know and solve. So Q equals, we know our mass is 10 grams. We know our specific heat is 4.18 joules per gram degree. And we know our delta T is 50 degrees Celsius. Okay? So all I got to do is multiply. Not so bad. So I punch this in my calculator, 10 times 4.18 times 50, and I get 2090, right? 2090, all right? And what are our units? Our units are joules. So how do we know our units are joules? There's a couple ways you can get here. It says how many joules in the question. Also, you can know that Q is going to be your energy, so that's joules. But if you include your units in your calculation, look what happens. Grams over grams cancels out. Degrees over degrees cancels out. And look what we're left with. Joules, right? So if you carry out your units throughout the calculation, you'll get your final units. And this is the answer. So we measured out exactly how much energy is needed to raise 10 grams of water from 45 degrees to 95 degrees. It takes exactly 2090 joules of energy to do that. Okay, so let's try one more, and then you can go work on the worksheet on your own. So number 2, so how many joules does it take to melt 70 grams of H2O at 0 degrees Celsius? All right, so a couple things to notice here. This little S stands for solid. So that's telling us water is in the solid phase. So now what is changing is our question. Remember, phase or temperature. So look for those key words or phrases that are going to lead you in the right direction. So our key word here is melt. So we're going from solid to liquid. So if we're transitioning between solid and liquid, we want to use Q equals MH sub F, right? So let's list our variables, Q, M, and then H sub F. That's one variable, heat of fusion, right? So what do we know? Well, we know we have 70 grams of substance. And because it's water, H2O, right, we can use table B, right? So we look on table B and we see our specific heat for our heat of fusion for water is 334 joules per gram, right off of table B on your reference tables. So now we plug in Q equals 70 grams times 334 joules per gram. All we're doing is multiplying, and we get Q equals 23,380. 23,380 joules. Okay? So that is our answer. How do we know it's joules? Because look, if you included your units in the calculation, grams over grams cancels out, and we're left with joules. So that's your answer. Okay? Now, what if I wanted to take those joules and make them kilojoules, right? What if I wanted to convert that to kilojoules? So that's my question. Let's think about what that means. Let's move that to another page. We got 23,380 joules, and we want to convert that to kilojoules, right? So kilo means 1,000, right? No matter what, kilo means 1,000. There could be a different unit, But the good thing about the metric system is that kilo always means the same thing. So 1 kilojoule is equal to 1,000 joules. It's 1,000 joules in a kilojoule. So look, 3 zeros. So most of the common units in science, you move 3 decimal places, right? They go in packets of 3 decimal places. So basically what you want to do is think about it and just use a little bit of common sense and say, okay, where's my decimal place? So here's your decimal place. It's at the end of the value. Anytime it's not shown in the number, the decimal place is on the end. So there it is right there. So I want to move 3 places. So just think about your units that you're using. A joule is a little unit, and a kilo is a bigger unit. Okay? So if you're going from a smaller unit to a bigger unit, so we're here. So we want to go 1, 2, 3. So this becomes 23,000. Oh, sorry. This becomes 23.380 kilojoules. Right? Or we can just write 23.38 kilojoules. All right. If we wanted to go the other direction, so let's say I had like 3.79 kilojoules, right? And I wanted to convert that to joules, right? I want to convert that to joules. So now I'm going from a bigger unit to a smaller unit. So I want to move 3 decimal places in the direction that's going to make the value bigger because there's going to be more of them, right? I'm going from a bigger unit to a smaller unit. So now I'm going to have more of them. So I want to go 3 decimals in the direction that makes the value bigger. So 1, 2, 3. So that becomes 3,790 joules. All right, so don't overcomplicate this. That's as hard as unit conversion is going to get in chemistry. You got to move 3 units, 3 decimal places, but you want to make sure you're moving 3 decimal places in the right direction. So if you're going from a smaller unit to a bigger unit, you want to move 3 decimal places in the direction that's going to make the value smaller because there's going to be less of them. And if you're going from bigger to smaller units, then you want to move 3 decimal places in the direction that's going to make the value bigger because there's going to be more units, right? It's like saying how many feet is it from here to the wall, all right? If it's 10 feet from here to the wall behind the camera, right? If I wanted to say how many inches that is, an inch is a much smaller unit than a foot, so there's going to be more inches from here to the wall, right? So that's how you do these heat transfer calculations. Hopefully that was helpful. Thank you. Bye-bye.